Hello, everybody. Welcome to another edition of WAVY Science Lab. I am meteorologist Jeremy Wheeler. There we go. And today we're going to be talking about ice. And we're going to be just talking about some different things about ice. We're going to talk about a little bit about the chemical nature of it, the structure of it. And then we're going to talk about some things that affect us, like ice storms, and talk about hail, things like that. So we're just going to cover all things ice today. It's called Ice, Ice, Wavy, a little reference to the song there, just a little play off of that. So hopefully you have some fun today and learn something. There's a few things I learned that I'm going to talk to you about that I did not know about ice. So let's get to it and talk about Ice, Ice, Wavy. So we're talking about all kinds of different things there. Some folks, love the cold. Some folks love warm weather. Some folks can't stand the cold. I've learned to appreciate it now that I'm older. I grew up in Illinois, and so I grew up where it's just, cold and cold all winter long. And so I got tired of it. So I moved down south, and now I'm kind of ready for some more cold again. So anyway, the water cycle, we covered that in a couple different podcasts. We're not really going to cover that much, but you can tell, evaporation, condensation, precipitation. Well, this is going to be just the ice phase of water. So we have these water molecules bouncing around a little bit. And they've got that 120-degree bond angle, right? And you've got the different pieces there, the hydrogen, 2 hydrogen, 1 oxygen. And so this time I brought in a demonstration. And so, here it is, water molecule, and it's bouncing around, right? You've got the 2 hydrogen, 1 oxygen. And so it's moving around in the atmosphere, moving around in the sky. And so these water molecules, as they bounce around, they break their external bond, then they reconnect. And so, when you have water vapor in the air, they're doing this a lot. When you have water, they're doing it a decent amount. And so, right, they'll latch on to another molecule and then they'll break off. And so that happens during water. So as the temperatures slow down, now this slows down. Instead of, these reactions of all that bouncing, now the bouncing stops and now it starts to really make that bond around 32 degrees, and the water starts to hold it together, and it makes this crystal structure. So this crystal structure, pardon me, I brought in some cool stuff today. High tech, really high tech. So now we've got the decaying structure here. Oh no, my structure. Well, I thought this would be very easy to get. Okay, so here we go. So now there you go, crystalline structure. And so they stack up, and then you get ice to form. So there you go, our ice structure. And now the big molecule I just had is now these little corners. Those are the water molecules. So they're bonding together. Okay, so the structure there. And I've used this many a times because I'm so proud of it, but we're not going to go through it as much as before. Just you got the warm air out there, the molecules bouncing around. These are air molecules, but you get the idea about the molecules. So then, and once they start slowing down, then they can start, latching onto each other a little easier. Okay, so let's talk a little more about that. So the crystal structure is less dense than water, because when you have water, they can start to kind of fit in those gaps a little bit. But when you have ice, then you literally have a lot more gaps in between, just the way that it is. And so that makes it less dense. And that's one of the coolest things about water. The water molecules, H2O, is just how that acts and behaves. So now you've got all these gaps in between the crystal structure, and now you can get that to do something really cool, and that is that it will be less dense than the water molecules if you have both together. So the ice is going to float on the water. It's time to do an experiment. Well, yeah, we got all kinds of cool stuff here. So let's do that. Let's do the experiment. We have a pitcher of water, and we have a jar full of ice. So place your bets, right? And let's see what we got here. Will the ice float on the water? Yes or no? And I think everybody pretty much knows. But let's see what happens here. So you got the ice that is... There we go. And what do you know? Now time for a drink. No. I know where this ice came from, but I don't know where the pitcher is. So so there it is, the ice floating on the top now. and you can see that clearly. And if I spill this, I think I'll be fired. So I got to be careful. So you had a lot of electronics. So the ice floats on top, and it's so simple, but it is a bit of a little experiment there. And now we have the proven that the ice does float on top of the water. All right. Thank you very much. Thank you very much. And where's my, there we go. Yeah. All right, so let's move on now, and let's go back to the computer. So, all right, we just did very simplistic things, which were a lot more difficult than I thought they were going to be. But so let's talk iceberg now. Iceberg, large chunk of ice that is broken off of a glacier or ice shelf, floating on water. And a glacier, right, is a very thick layer of ice that builds up. But anyway, an iceberg, I didn't know this, that it has to have a certain criteria for that to be considered. A height must be greater than 16 feet above sea level, right, where we meet the water line, and the thickness must be 98 to 164 feet. So that's very interesting. I didn't know that. And it must cover an area of at least 5,382 square feet. Okay, I thought they were just, iceberg is an iceberg is an iceberg, but it's not. And so this is a giant iceberg, and this was from NOAA. And look at that huge thing. I mean, it's amazing. Can you imagine seeing that, actually being there and going out witnessing that? I've seen meteorologists go around it, and scientists, in boats and stuff. And then just to be careful, because those things, sometimes they roll and turn and have that, create some, water splashing up. It'd be cool, but it'd be kind of a little scary. Anyway, the smaller pieces are called bergy bits or growlers. And this is from also from NOAA, Ocean Service. Bergy bits, higher than 3 feet, but less than 16 feet. Okay, cool. Growlers are small size, which compared to you and me, they're big, but smaller size of a truck or a grand piano. So that's fairly big, but compared to the actual icebergs, they're much, much smaller. And then the tabular means that they have steep sides with a flat top, non-tabular, different tops, domes, spires, things like that. So there's, just some information that I never knew about icebergs. Of course, I've never even been around one, but now I know. And then they're monitored through MODIS, Moderate Resolution Imaging Spectral Radiometer. And I believe this is in the visible, so we can see it like we're seeing it on satellite, but it might be a little bit infrared too. I'm not sure about that. But anyway, it's on NASA's Terra satellite. All right, so this is all about icebergs. We got a lot more to talk about with ice, believe it or not. There's a lot of cool discussion here from myself, but we'll go more into this in just a little bit. Stay with us. All right, we're back, and I want to talk more about ice. We covered icebergs, the structure of it, things like that. So let's talk a little more about some things. Also, the icebergs. Ice is monitored by the U.S. National Ice Center. Didn't know that either, including the Chesapeake Bay. They do cover us. They're not very busy when it comes to our region, but if we do get ice on the Chesapeake Bay, they monitor it. And only organization that names and tracks all Antarctic icebergs. So I don't know how many names there must be thousands and thousands of those things. So maybe they give it numbers and names for the bigger ones. I don't know, but yeah. So now the sea ice and the all this ice in the north in the Arctic affects the jet stream. So, that it acts like a cold battery, and you store that cold up north. Well, the thing is, as you know, the Arctic ice has been shrinking more and more and more. And so we're getting these destabilized zones. We're getting more of these, what do I want to call them? Just kind of blobs or nodules of cold bouncing around. And so now we're getting, more instability, and we're getting these colder shots that come down. We always had colder shots, but I think it's becoming more common to get these warm blobs to move up into the Arctic this time of year, or in the wintertime, and then pushes the warm air goes up, so it pushes the cold air down. I think we're just seeing more of that, more instability, more kind of wild weather. A couple of years ago, I think there was something like the temperature in the Arctic at North Pole is like 50 degrees, way above average, and then all that cold air rushed down here. So anyway, so that's in terms of the jet stream. So now let's talk about history and the ice ages. An ice age is a period of colder global temperatures and recurring glacial expansion capable of lasting hundreds of millions of years. We're talking about very large scale here. 5 significant ice ages in Earth's history, about a dozen epochs in between. Well, not between, but yeah, in between ice expansion in the last million years. And colder temperatures, what happens is, so the snow doesn't melt. You get such cold air for such a long period of time, the snow doesn't melt, it compacts, and those layers of snow build up, and eventually, there's a lot of weight there. And so it compacts that bottom, and the pressure causes that to form into ice. And there might even be a little bit of melting happening and refreeze, maybe a little. But, bottom line is just it becomes ice. And so the last ice age peaked about 18,000 years ago. And then we've had the Holocene, which is kind of a stable period since for the last 11,700 years. And then there was the Younger Dryas period too in there. So, there was a pause. But anyway, at peak, it grew 12,000 feet thick. Can you imagine that? 12,000 feet? I mean, thick, high? I mean, that's just crazy. And it covered Canada, Scandinavia, Russia, South America. Was that North America? Maybe I misspoke on that part. But there might be part of South America, but definitely North America. I think I put South in there. Anyway, sea level dropped 400 feet. 400 feet, the sea level, because, it was all stored in ice, and a lot of it was. And the temperatures dropped about 10 degrees. You think about that. I mean, an average of 10 degrees for the globe. That's a huge number. And so then in the 19th century, Swiss geologist Louis Agassiz studied rock striations in sediment piles. And so he found evidence of glacier activity from destructive winters. And in between these layers, he found plant life in between. So he theorized, that there were these ice ages. And then in the 1940s, Serbian mathematician Milutin Milankovic, he came up with the theory, and he calculated all these different things when it came to the sun, solar activity, and orbital variations, eccentricity, precession, axial tilt, how the Earth is tilted a little bit and how that changes. And so he calculated that there'd be these colder and warmer periods. And so he charted the ice ages for hundreds of thousands of years, and then they used this and went back, and expanded it so millions of years. So we got a lot going on here. Let's explain. So these are the ice ages. The longer, where a huge amount of the Earth was just covered in ice in these 5 periods. And you can see there was one just recently. We had one, and then about 350 to 260 million years ago, 460 to 430 million years ago, and then in the timeline again, not to scale, but and this is from the Utah geology group. So, and you can see then more than millions of years ago, there were some more of those. And then there were these smaller ones. This goes back, 400,000 plus years. And so you can see these glacial periods in there. And so these are the epochs that we were talking about, and your glacial periods, and just, pockets of much colder air. So this may not have covered as much of the Earth. It did not cover as much of the Earth as an actual ice age. But still, I mean, it did affect a large area. And then, in more recent times, they studied the sunspots and sunspot activity and how that affected climate. They went back, look at tree rings, ice core rings, and they put all these pieces together. And so they found out that, when you have some of these periods of lower solar activity as well, not just, the precession and all the different orbital angles, that lowers the temperature of the globe. So there was the Maunder minimum when they had a very quiet period, 1650 to 1700. It was colder then, and then the ice age, the mini ice age in the 1300s. That was another time that they had a lower sunspot activity. So then the ice in the north grew, but it didn't grow to the levels of some of these epochs and the ice ages. So now let's talk a little bit about precipitation types. We covered the water cycle. We covered rain. We covered these things in the past in another podcast. But so you got, all that warm air. You got the water cycle. You get rain. You've got maybe a cold layer, and you'll get some refreeze, so sleet. And then you got all cold is snow. We had a whole podcast on snow, and I don't know what that truck's doing. It stops. I'm not going that way, and he backs up. I don't know, but so those are four or three different types. But the fourth one is freezing rain, and we're going to talk a lot about that. So freezing rain is when you have liquid water falling, and then it falls through a colder layer, and maybe the ground is frozen, and so you get freezing on contact. You get grapple to form. And so the difference, I think, between sleet and grapple, which is also ice, is that sleet is like tiny, hard little ice cubes. Grapple's tiny, softer, maybe like more like styrofoam balls, kind of. So that's kind of the difference between sleet and grapple. So the freezing rain, you get the warm layer aloft, sub-freezing layer near the ground. We're going to pause here. We're going to go into this in more depth in just a little bit. So stay with us. All right, we are back and talking about ice. And so let's go back and talk about that freezing rain, because that's where we left off. And so you got a warm layer aloft, sub-freezing layer near the ground. The temperature at the ground might be 30 degrees, 28 degrees, what have you, the air temperature. The ground itself may be frozen as well. Maybe the ground froze the night before rather, and it's running 32 degrees. So that liquid water will hit that. Doesn't bounce like sleet does. It'll freeze on contact. We got rhyming happening. So there you go. You got this layer above 32 degrees. Sometimes a warm front, the warm air in the upper levels will kind of get above and move north of the look, I'm doing Tai Chi. It gets above and ahead of the cold air, and so maybe the cold air at the surface, and the warm air above, there'll be rain, and so then all of a sudden you've got freezing rain, freezing on contact. So some historic ice storms. Wrong way. The December 4th, December 5th, 2002, East Plains to the Midwest, the Southeast, there was an inch of ice over parts of North Carolina even. 1.7 million without power, so that was one. And then January 26th through the 28th, 2009, Arkansas, Kentucky, Missouri, 1 to 2 inches of ice. 1 to 2 inches of ice on, a layer of that. Think about that. That much ice. 1 to 2, that much ice. Trees fell on homes, 1.3 million without power. My dad was through that one, and I remember him talking about it. He said he was so scared because he kept hearing ice crashing, trees crashing, and he was worried about when crashing into his house. And he was so scared with that. So that was 09. 1994, a little ways back, February 9th to 13th, Southeast states, $5.7 billion in damage, 2+ million people without power. So that was a pretty bad one, and that's, I think, unadjusted dollars. So one of the worst ones then in modern history is this one. It was 1998. I was around for that one. I remember it. One of the worst in history. Over $3 billion in damage, 40 fatalities though, and millions with no power. The thing is that the size of the area that was struck was just amazing, and about 3 inches of ice in some areas. Think about that. Even up to 4, I think, in some. So some regions, the thing is, they took weeks to recover because there was so much damage in the power lines. And so again, I remember that. It was bad. And then what we're looking at here is some of the thickest ice areas, parts of New York, a little bit of Vermont, Maine. But those darkest blues, 100 millimeters, that's a little less than 4 inches. So, I mean, that's just, wow. And then I believe there was even more area covered here. I think maybe that's the worst of it, because if I remember right, I mean, it covered an expanse. And so, but yeah, that was one of the worst in history. There's a photo from NOAA. And yeah, it was just like that. Look how thick the ice is on those trees. And it just weighed the trees down and blammo, they just, they fell on things. All right, so that's cold weather. Let's talk about some warm weather ice. Yeah, ironically. So this is hail. So with hail, you get these updrafts, and the water droplets, there are water droplets, they go below that freezing level, and they bounce, and so they'll go up and down, up and above, and they'll melt and freeze and melt and freeze. You get these layers of ice in there, and then eventually they get heavy enough that they overcome the updraft and they fall out of the thunderstorm. And you can get hail all different sizes, pea-sized hail. You can get nickel-sized hail, quarter, golf ball, baseball, softball, grapefruit sized. So yeah, you get these different sizes of hail, and they can cause damage. All right, so you can also get another thing to happen in a freezing fog. We've had that here. This is an extreme case, courtesy of NOAA, but we've had freezing fog around here even kind of recently. Didn't cause any problems, wasn't anything too big. Now, sometimes the ice will freeze, and so, this is more for up north than here. A lot of times here, the ice doesn't get this thick. Maybe on some ponds, maybe after like a week of temperatures in the 20s, yes, maybe you can get 4 inches of thickness on the water, on top of the water. Then, yeah, it's somewhat safe. 5 inches. And you need to, if you're a kid, hey, always ask an adult, always, have an adult out there and make sure it's safe. Have them tell you it's safe. But yeah, I mean, driving on 8 to 12 inches and then trucks 12 to 15. Ice Road Truckers, right? The old show. My son used to watch that. So now we go into de-icing planes. The plane is, the surface is cleaned and de-iced with glycol water mix, kind of like antifreeze it's used. And so it's heated and sprayed through a hose and shortly before takeoff. And then it can refreeze. So the holdover time is important because I want to make sure that they get up in the air and going and there's not, it doesn't refreeze before they take off. So they de-ice the planes, probably anti-icing the planes. They use the same type of fluid with a higher concentration of glycol and chemicals that's thicker. Thickening agents added. They put this on the wings, the tail, the engine is, so that the ice doesn't form on the planes when it's up there. But I didn't know that. I also didn't know that the pipes carry warm air from the engine to the wings and tail to keep that ice from forming. And some aircraft use small inflators to break up the ice. And I'd love to know more about that. But for the sake of the podcast, I just took it to add value. But yeah. So new research from poison dart frogs can change the future. They make possibly super hydrophobic water, right? It doesn't mix, it doesn't collect, it rolls right off the plane and doesn't stick to the surface. So an antifreeze is released from the inside of the plane in small little batches there. So that's something that they may use in the future. And this is NASA. They're de-icing their plane there and using a truck to do it. So very cool. That's an aircraft. And then you can get black ice to form. Black ice, just, you get water to freeze. And so it's not truly black, it's clear, but on black top, which happens a lot, then it can appear black and it's hard to see. It's hard to make out. And then you can get a melt and a refreeze, and you can get mixes of ice and black ice and dry spots. So that's a problem that we have here in Hampton Roads quite a bit. You get a refreeze to happen. And then, you can also get these flash freezes, which cause black ice. The temperature can plummet overnight, maybe dropping down to the 20s after a rain the day before, and then you can get that big sheet of ice and big problems from that. So it's not like freezing rain because it's just rain, but then it freezes. So that can happen. All right, so let's talk about the environmental tip of the day. It does tie into this. Try to limit salt use to break up the ice on walks. And you're going to use it, that's fine. It's sanctioned, everything, but just try not to overdo it. Just don't go crazy and say, well, there's a little ice out there, I'll just cover the entire walk. Think about that. I mean, that stays out there, gets into the ground, and it can run off and go into the sewers and things like that, and causes corrosion on vehicles too. And rock salt can contaminate water and harm plants and wildlife. So that's just some advice. All right, hopefully you learned something today about ice, a couple things I didn't know. And very cool stuff. We did a couple experiments. One was not so great, but hopefully you had fun watching me mess that up. So, all right, everybody, stay cool and pun intended, and have a good day.